Okay, so let's continue with those SDR. So here you will really see the formulation, the more proper formulation of this semi-definite relaxation. And semi-definite relaxation is very helpful in problems of these forms. So I have a quadratic program with a quadratic constraint where I have my C here is semi-positive definite. The AI is semi-definite positive. Actually, here the I here should be removed. It's just X Hermitian. So AI is semi-definite positive and C is semi-definite positive. Right? So this is a very interesting problem. Is this convex? So C is SDP, AI is SDP. Remember, that's what we needed to have convex quadratic program and convex constraint. But something has changed here compared to what we had before. This quantity, I don't write this is smaller than BI, this is larger than BI. Right? So what does that mean? So you remember what we were saying? If you have this kind of quadratic objective function or quadratic constraint, it looks like an ellipse. Remember? So you get an ellipse, and if you have X, AX smaller than B, essentially you have all the points that typically within that ellipse. Right? And this is actually convex because you take any 2 points, you draw the line, and this line is still within this set. But now I have XT, AX is larger than B. So I have something that is quadratic like this, right? And instead of looking at the bottom of that valley, I'm looking at all the area above a certain level, right? So now I'm looking at this area. So if I take any 2 points here and there, and I draw a line, those elements here do not belong to that set. So this exterior part is non-convex. Okay? So why this is interesting is for the following reason. This could be an example, for instance, where you want to transmit a stream of information to one user, not to one user, a stream of information that is common, that is the same for all the users. So for instance, all of you here listen to me, so I have one message to deliver to all of you. And all of you have to understand with a certain quality of service, a certain SINR. And this is what's happening here. The SINR for each of you has to be larger than a certain constraint. And this SINR or this SNR, in this case will be more an SNR, you will see. So the SNR of each user will be larger than a certain constraint. This SNR will be a quadratic form. But it says that essentially each of you will need to receive at a quality better than something. And so this is represented like this. Each of those ellipses here is one of those constraints. So this quantity here represents one of those ellipses. And I have multiple of those constraints. So I create multiple of those ellipses. And I'm looking at all the areas outside of those ellipses, right? So all the area in gray, right? You take any 2 points in this gray area, you draw the line between those 2 points, clearly it still doesn't go through the gray area, so it's non-convex, right? So this is clearly a problem where you have a quadratic program, the objective function is quadratic, the constraint is quadratic, but you don't have a smaller or equal, you have larger than equal. So this is a non-convex QCQP, non-convex quadratic program with quadratic constraint, right? If I go back to what we had before with QCQP, right, so here, imagine that I remove this. I remove this, I remove that. This is what we did last 2 weeks ago. I have the same expression here. This is convex if this is semi-definite positive, but I have a negative there, right? So that means that I'm looking at, if I represent this, and I had a figure, I think, somewhere, not this one. Yeah, I mean, is this example here, where this is my quadratic program, objective function, and this one I had linear constraint, but instead of having this, now I have an ellipse. But I'm looking inside that ellipse, right? But now the new problem I'm looking at is I'm looking outside of those ellipses. And so here I was looking inside, so this forms actually a convex set, because any 2 points here any line between any 2 points will still be within that set. But if you look at now outside of this, the outer part is actually non-convex because you take any 2 points, and any lines between those any 2 points do not belong to outside this. They have to go through inside, right? So it's the same problem as, for example, if you go back to the illustration we had here, right? This one here, right? This is non-convex. You take any 2 points and you trace the line. Any points here do not belong to that set, right? So here we have the same problem. We have a non-convex quadratic constraint, quadratic program with quadratic constraints, right? And this is what is represented here, where you have to optimize an objective function. Those are represented by those lines, those blue lines. Those is actually the level of my objective functions. And this, forms an ellipse because I have a quadratic program. So I have something that is like this, a kind of a ball. But then I have to minimize that function subject to being outside the white area. Okay? So how do you do that? Well, you can formulate this as an SDP or an SDR by saying this quantity here is, I will write this again, this is X Hermitian Cx. So this is a scalar, so I can say this is a trace of this, right? And then I bring this here, so this is the same as saying trace of X Hermitian C. And then instead of optimizing C, I will create a matrix big X, and I will optimize the trace of X multiplied by C. And I will say, but careful, I need to make sure that the rank of X is equal to 1 in order for this formulation to be the same as this formulation. Right? And then, to solve it, I will ignore this constraint. I will find X, and I will do some manipulation on X to try to recover a rank 1 solution. Right? So this is what you see here. This problem is strictly equivalent to this one. It's not the same optimization problem, but it's equivalent in the sense that the solution here of this problem will actually be the same as the solution of that problem. Right? The objective values will actually be the same. So you have a quadratic constraint here, a quadratic objective function, a quadratic constraint. You transform this now into a form of linear objective function, because instead of having x and x there, you now create a matrix x. You have linear into the entries of x here, but now you have a constraint on the semi-definite positiveness of x, right? Because this quantity is semi-definite positive, right? That means actually the eigenvalues of this are always positive or equal to 0. And this is the case. So this is indeed semi-definite positive. But this is semi-definite positive with rank 1, right? And what we say is, let's abstract this into an x that is still semi-definite positive. That's what we have here. But I have to add the fact that it's rank 1, right? So this combination, those two, would then tells you that your x can be written as x multiplied by x Hermitian. That's what it says. Okay, so linear in x, trace constraints are linear inequalities. And so in CVX will not like this. You're going to have to write this as linear inequalities, linear equalities. So you're going to have to use a slack variables. We'll see this in a minute again. So same as what I wrote there. And then you have this. So all of this, if I remove this, this is an SDP. This is a convex problem. Linear, this is a convex cone, because the set of semi-definite positive matrices is convex. So this is, but this is non-convex. So this constraint is non-convex. And the reason is non-convex is because if you take any two matrices, and imagine I have x and y. If it's convex, that means actually I take x and y, and if I take just a simple linear combination of them, it will still be convex, right? So if I take the rank of x plus y, well, even though the rank of x and the rank of y are rank 1, the rank of x plus y is not necessarily rank 1. That's the reason why this is a non-convex constraint. And so that's why the way you do that, you ignore this first. And then you see what you get. And this is what we did in the previous example, right? Where we had this here. We actually did not write rank of BI is equal to 1, because by chance, the solution here is rank 1. But in general, it's not true, right? For that specific problem, it was rank 1. But so this is the proper writing formulation. You do that, and then you say, okay, let's ignore this. And you solve the equivalent SDP by ignoring this. Right. And then after this, you check what your solution is. And if your solution is indeed rank 1, then you're good. Right? You solve an SDP that is without the rank 1 constraint, but the solution actually has a rank 1 constraint. So you're good. So your optimal solution, if it's rank 1, it's fine. You just do an eigenvalue decomposition of your x. Essentially, you're going to write this x as a product of two vectors. Vector multiplied by this Hermitian. That's all good. Now, if x is not rank 1, then you have multiple methods that can be used, and those methods depends on the problem formulation. So I don't give you here a general solution, but one solution is to do what is called Gaussian randomization. So you view x as a covariance matrix, and you generate vector x here. You generate those vectors, that has for covariance matrix that have this. So you use, for instance, you generate vector x that are Gaussian distributed, whose covariance matrix is equal to that, and you generate many of them, and you try to find by chance, one of them that satisfies all the constraints that we have in the objective function, that satisfy all the constraints. But and you choose the one that minimizes the objective functions. right? So this is something that you will see in this paper, but this is the general way it works. So you generate random samples, typically with zero mean and a covariance matrix X. This is obtained from your semi-definite relaxation problem. So this one is coming from CVX. Then once you have this, you generate many samples, a bit like when you generate MIMO channels. You have a covariance matrix or correlation matrix of the channel, and you generate channels with that correlation matrix. Here you do the same thing. They're Gaussian distributed with a certain covariance matrix X. And you play with those samples typically such that your constraints are satisfied. So if you just generate those samples, they may not, in general, satisfy the constraint of your optimization problem, so you may need to scale them. And then you choose the one that actually minimizes the objective functions. And the larger the number of samples you choose, the higher the accuracy, but the longer the computational time. So I will show you an example here. So let's look at this example here where we do, this is my second example, I do MIMO detection. And I will use this randomization. So I do MIMO detections where I have to do these ML detections, for instance, where I have a receive observation, I have a channel matrix H, and I have a transmit signal vector C. And I'm constrained because the entries of SC are QPSK entries. Okay, so this is maximum likelihood. And when you do that, typically, you have to go over all those combination of entries and find the one that minimizes this quantity, right? And we're saying this actually, the computational complexity is exponential. So what I want to do here, I want to, instead of using maximum likelihood and do an exhaustive search, I want to formulate this differently such that this looks like an optimization problem, and we can solve this using semi-definite relaxation, right? So that would give you an alternative solution for receiver design compared to the classical ML strategy and zero forcing and so on. So how can you do that? The first trick is to say, well, those are complex entries, so I will write this using real entries. And so I create the Y and the S actually obtained by stacking up the real part and the imaginary part of my SC. So by doing this, I create S. And I do the same for Y. And you can write this quantity exactly in a different form, but exactly equivalent as using this, where now each of those entries here is essentially real, right? And this is what I have is, this is actually classical formulation. Your H, sorry, it's not HC here. Sorry, it should be Y, should be S, and should be H, right? So this quantity is the same as this, right? And now my S, they're only between only +1 or -1 is not +1, -1, plus minus J, is just real quantities, right? So this formulation is actually the same as this. So you convert complex quadratic objective functions into a real value one, right? And now we want to write this something that is equivalent to an SDP. So how we do that? We want to expand, and we want to write this something that looks like what we had here. This one, once we have this, if we have a formulation that looks like this, then I can do those steps to have something like this, right? This is what I want to get to. And so I take this objective function and I expand it. And I expand it, but expanding it, you see you have multiple terms. And those different terms, they actually, what you would like is to have a form that is something like this. Because then you have something that you can write easily like that. But here you have some additional terms. And that's the reason why we introduce a variable t here. And I will not go into all the details, but this t has actually a certain constraint, so that actually this t, the magnitude is actually equal to 1. But the nice thing is that when you introduce this t, this quantity can now be written as a form like this. So I introduce, on top of S, I introduce a t, so that now I create a vector that is slightly longer, But by doing this, I can write my original objective function here as something that looks like a homogeneous QCQP. So what that means, homogeneous here, is that I only have this XTQX formulation. I don't have those other terms like this that are only a function of X or a function of X Hermitian or something. It's only this part, right? And this is very nice because this is something that is reminiscent of that steps. So I can do those steps and I can say, no, oh, this is my objective optimization variables, but I will write this as a trace of this. This I will bring to the other side, and I will create a new matrix X such that this X ideally should be equal to X multiplied by XT. Right? So this is what you do here. You reshape, and you see this reshape of the formulation can be very much problem dependent. And this is where you need quite a bit of experience when you play with convex optimization problem, is to do this progressive transformation. And so what is nice here is that you end up with a formulation that says, well, I have a linear function in the entries of X. I have a constraints on the entries of X, because the entries of X, the diagonal entries of X here are actually have to be equal to 1. And why they have to be equal to 1? Because the diagonal entries of X reflect those constraints that we have here. All the SI square have to be equal to 1. Why they have to be equal to 1? Because that comes from these constraints on S here. S square has to be equal to 1. So this quantity, the fact that S is binary, plus minus 1, this is converted into a constraint that says, instead of playing with those binary variables, I'm just saying S square has to be equal to 1. This is my constraint, right? And this is what you see here. I have my S square is equal to 1. So I have written my objective function slightly differently, my constraint slightly differently as well. And now I formulate into something that is closer to this SDP formulation, because this quantity now is equivalent to that, with the constraint that the rank of X is equal to 1. So if you take this SDP, this semi-definite positive constraint, and the rank 1 constraint together, this would mean that X can indeed be written as X multiplied by X transpose, the same way as what we did before, right? And so what you end up with here is a non-convex optimization problem. But if you can solve this, you end up with another receiver architecture for MIMO detections that is based on non-convex optimization, right? And how you solve this? Well, you use CVX by first solving this. Those are linear constraints. This is your SDP constraint, so definite constraint. This is linear in the entries of X, but this is non-convex. So you relax this. So you solve an SDP problem, and then you do this randomization that I explained before, right? And if you do that, then you can apply this case, for instance, where I have a MIMO transmission, 2 transmit antenna, 2 receive antennas, and I use QPSK for the 2 streams, right? And what you see here is that you end up with performance that, for instance, at 20 dB, you are roughly at a bit less than 10 to the minus 3. Okay, so how does that compare with what we had before? Where is that? Right, here. There's the same. That's QPSK. So 4 bits per second per hertz. And at 20 dB, we are at a bit less than 10 to the minus 3, right? So we are here. Right? So now I have an alternative detection strategy that relies on convex optimization by saying, instead of solving the original maximum likelihood problem, I convert this differently into a form that actually looks like convex after relaxation, and I use convex optimization tools to actually design my MIMO detections. And you end up with performance here that is very close to a pure or exhaustive search that you would do with classical maximum likelihood, but very likely with lower receiver complexity than doing the exhaustive search. Okay, so this is an example where you can really use this to do maximum likelihood detection. So instead of doing the precoder design that we were doing in the previous example, you do this now for receiver design for MIMO detections. Okay? And so people have done this. This is the examples how you formulate for QPSK, for instance. People have done this for larger constellations, right? So it's a bit more complicated how you need to formulate the problem, but essentially, yeah, people have looked at that. Okay, so this is an example of how you can use SDR for MIMO detections. Okay, so let me give you another example of SDR. Now when we do this multicast beamforming, and this is really maybe the primary motivation of using DSDR in communication, is a very well-known example. So of this problem, this is actually very reminiscent of what we have when we do multicast transmission. And so multicast transmission is not the same as the example I had here, because here I assumed every time you transmit one independent streams from each other. The multicast is when you transmit one message that is intended to all of those users. So that's the example I gave you before. I talk and you all listen, but you all want to have a quality of service that is higher than a certain threshold, right? Okay? So this is what we have in communication, and this is what you do, for instance, when you do and in BBC, when they broadcast information over a 5G network, for instance, they transmit, a BBC news, but this news has to be encoded at the rate such that it's decodable by all of you, right? It's also reminiscent a little bit to the problem we had when we were doing superposition coding. You remember when we were doing superposition coding on the broadcast channel? So we had the message of the weaker user had to be decoded by both users, right? So that means actually this message has to be transmitted at a rate so that it's decodable by both users, right? So here we do this. The problem is we have multiple antennas there. So it's not simply like in the broadcast channels where we have single antenna and we make sure that actually the message is decoded by the weaker user and the stronger user. We have multiple antennas here, but the precoder, and I have only one precoder, one vector, has to be designed such that the SNR here is larger than a certain threshold, the SNR here is larger than a certain threshold, the SNR of all the user is larger than a certain threshold. Right? So it's the different formulation from the unicast one. In the unicast, you had one beamformer per messages. And each user were intended to decode his own message. Here you have one beamformer, but all the user wants to decode that stream. Okay, so here, this is how the way it works. I want to minimize the power used at the transmitter. So I have a minimize of the norm square of that precoder, which is the power at the transmitter, subject to a constraint. So what that means here is that this is the SNR typically at each of the users. If each of the users have, each of the users here, I transmit one message, each of the users can compute an SNR, and you want this SNR to be larger than a certain threshold. This is what we have here. This is actually obtained by doing maximum ratio combining, assuming you can have potentially multiple antennas at the receiver, at each of those receivers. So if you like, this is, if I draw this, if I have one beam, I transmit along W, I have, like, say, one beam, but I may have multiple antennas here, right? And so the challenge to user, let's say, user 1 is my HL. I have that HL, and the L belongs to II. II is the set of antenna of user I. Right? So what that means here, HL multiplied by W, this is the effective channel here. As you see here, at this receiver observation here, I have Y will be HLW plus some noise at this receive antenna. And plus the transmit signal that I transmit C. And here I'm going to have something slightly different because my channel is different. Right? So this is my effective channels, HL multiplied by W at each antenna. And then I do MRC. So after MRC, I will have a sum of the magnitude square will be my essentially SNR after MRC. In the same way as we had, you know, if I had H1, H2, H3, and I had 3 receive antenna, I had H1 square plus H2 square plus H3 square. Remember when we were doing MRC and I had only a single antennas here, right? Now I'm doing the same, but I have a precoder here. So I have my effective receive channels after precoding at the receiver. Here is HLW, and I have here another HLW here because the channel is different. And so I end up with essentially now an SNR after combining, which is the sum of the effective channel, right, across all the receive antennas of that users. Right? Good. So now we can write this as an SDP and then relax it. Same trick. Again, this will be written as a trace of WW Hermitian. And this one I can expand this, right? And this one I can expand this. And if you expand that, right, you have something like this. A sum over L of HIW, right? So this is a sum over L of, I can write HI Hermitian W Hermitian, HI Hermitian W, right? So this is a sum over L of W, H, HI, HI Hermitian W, right? This is one way of representing it. And so this is the sum of WH sum over L of HI, right? So L belongs to II of HI Hermitian W, and I create a matrix there, right? And this is that matrix here. And it's obviously L here, right? It's not I. Okay, so now I create a matrix here, and I have my W there. Right, so I have my H, and now I have my B, and now this is same trick as before. This is the H. I call this H. It's called HI there, right? HI. And now this is the same. I think this is a trace of WH, HI, W. And now this is trace of W, WH, HI. And this is a matrix. And I'm saying this is Hermitian, this is semi-definite positive. It has a rank 1. So I will write this as a semi-definite matrix. That's my B there. And I will impose this to be rank 1. This is my rank 1. Okay, same trick again. Now how you do that? Again, you relax this. You solve it without doing that. You have a classical SDP. And then you do randomization. And so this is an example of how you do that for this problem. When you have this power minimization in multicast, and then after doing that, you need to do now this rank 1 approximation or rank 1 randomization. So you need to make sure that your X that is obtained is actually rank 1. And you need to create essentially randomization vector X or vector W that are now rank 1. And so this is what this operation is done here. Right, so let me show you some examples. So here when you do this multicast beamforming with power minimization, so I have in red, I have two transmit antenna 10 users. In red is what you get with this SDR upper bound. So what that means is that is when I solve this problem without the rank constraint. So if I remove the rank, I'm relaxing the problem, so I'm removing some constraint. That means that the objective value can only decrease, right? You remove some constraint, that means actually you can do better, right? That means that your objective value should decrease if you remove constraints, right? You can further minimize it, right? This is what you see here. If I do SDR upper bound, is actually by removing this rank 1 constraint. This is the bottom, the red one I can achieve is always the lower bound on the performance or the upper bound depending on how you see, right? The randomization is when you actually take your X, right, or take your B here, you solve it, but then you reconstruct a W that is rank 1, right, based on, by doing this randomization, by generating Gaussian entries for W whose covariance matrix is equal to X. And you take many of them, and you choose the best one. And this is what you see here. You have 100 randomization, and you see that in blue, you don't get exactly the same as the red one, because the solution here actually satisfies the rank 1 constraint, but is not the same as the optimal solution of the problem without the rank 1, right? So it's coming close to it. And the green one is when you do another form of actually randomization, is a rank 1 approximation. What this does is the following. You have a solution of this B there, right? You have a solution of this B, and what you do is that you build your W by taking the dominant eigenvector of this. So your B, if you do an SVD decomposition, you can say this could be something like lambda I multiplied by VI Hermitian. Those are the eigenvector of B, and those are the eigenvalues. And I'm saying I'm approximating this as a rank 1 matrix. So I'm saying this is roughly the same as just lambda 1, V1 Hermitian, where lambda 1 is the dominant eigenvalue, right? So this would be the rank 1 matrix that is the closest to your original matrix. This one the solution may not be rank 1, unfortunately, but you choose the solution that is the closest, but that is rank 1. And you obtain this by choosing only the dominant eigenvector, right? That's that solution. That rank 1 approximation. And the problem with this is that sometimes it works well, but sometimes you see you don't have this green cross, like here, those channel realization. And the reason why you don't have those green cross is because by doing that, by now creating your W, so your W now will be what? Your W will be square root of lambda 1 multiplied by V1. This would be your W. Right? By doing this, you do not necessarily satisfy the constraint anymore. You do not necessarily satisfy those constraints or those ones. You have generated a solution. This one is all good when you generate based on B, but now that you're forced to be rank 1, you may not satisfy the original constraints. And so you have to check it again. And so sometimes it does not work. So that's what you see here. This solution of rank 1 approximation is okay for some channel realization, but sometimes it's not. You don't have a solution because the solution does not satisfy the constraint, the original constraint. Right. Good. So let me show you another example, which is the opposite problem. So namely, I have now a power constraint, but I want to maximize the SNR of all the users. Right? So before, Remember here, I wanted to minimize the transmit power constraint subject to SNR constraint that is larger than something. Now I want to do the opposite. I want to maximize the minimum SNR among all the users subject to a constraint on the power. It's a different problem, but it's closely connected. So that's why I'm saying, now I want to maximize your minimum SNR, but subject to a power constraint. So you see the difference? Before I was saying, all of you need to satisfy a certain quality of service, and I will minimize my voice. So that is, essentially, you all have to understand what I'm saying, but I will decrease my voice level till you don't understand anything. Now I'm doing something different. I'm saying I fix the level of my voice, and I want to make sure that you all maximize the minimum quality that you get. So the worst listeners should also, this quality should be maximized, right? So it's slightly different formulation. So how you do that? It's a max-min problem. So you want to maximize the minimum among the SNR of all the users. And so how would you write this down? You can say the following. So max min over I, hi Hermitian, right. So let me write this slightly differently. And I will say this is a max of a new variable t. I want to maximize this subject to the minimum over I of hi Hermitian w has to be smaller or equal to t. I don't change any, I mean, the problem changed, but actually the solution will be exactly equivalent between this one and this one. If I maximize t, I will push the minimum up, and so that will be equivalent to maximize the minimum there. Right? Now this one, I can write this equivalently as maximize over t, and obviously I have the w there everywhere, right? Maximize over t of subject to, what is the minimum? I can say this is hi Hermitian w square has to be larger or equal to t for all I. So you have, instead of having one constraint, I'm now writing this as multiple constraints. The minimum has to be larger than something, so all of them have to be larger than something. Right? And once I have that, then I can say, well, max of t, this is equivalent to minimize minus t, subject to the same constraint. Right? And so this is what you start seeing there. Now you have a minimizing of minus t. And now this constraint, you start being familiar with that now. This can be written as equivalent as a trace of x multiplied by hi. Because you're going to have w and w Hermitian, and I will say, okay, this will become one matrix that has to be semi-definite positive, and it has to have a rank 1, so I end up with all those constraints appearing. Okay? Same trick, remove rank 1, solve the problem, get your x, and then create your vector w that, based on randomization, that have a covariance matrix that is equal to x, and you generate multiple realization of this. And so this is what you have here again, is you have now your objective value is max min, so you want to maximize this quantity. So SDR upper bound is when you relax the problem, you don't have the rank 1 constraint, and the blue and green one is when you do this randomization, and when you have more samples, essentially on average you do better, essentially. That's why you see on average you see the blue one is better than the green one, because essentially you have more samples to pick up from. Okay, so this is the idea. And so you can change the parameters. You see, you increase the number of users, for instance. And so if you increase the number of users, well, it becomes a little bit more difficult. So they have a larger gap also between the upper bound and the randomization. If you increase the number of antennas, the gap between the randomization and the upper bound becomes even bigger. It's even more difficult to close the gap. And so you can change the parameters like this, and you see how far you are from this upper bound. Okay, so this is an idea of how you can use this for this multicast problem when you want to maximize the minimum rate among all the users. Okay, so let me go through this before we stop today. So this is about RIS, so Reconfigurable Intelligent Surfaces. This is the topic you're going to have in your coursework 3. This is a very popular research area also for 6G, and the idea is the following one. So far we have looked at a transmitter, a receiver, and we had a wireless channel. And these wireless channels, typically we assume maybe it's known, and then we adjust the transmitter and the receiver according to this wireless channel. Now what we want to have in the future is, for instance, you have on the walls, you have passive elements that you can control. So passive means they do not contain oscillator and power amplifier. They just act as a kind of reflector, but smart reflector. So they consume very little energy, but you could have elements that are placed inside the walls, for instance, and when the wave impinge on those elements, essentially you're going to have, for instance, a phase shift such that all those elements will work together to try to reflect the wave in the directions of interest, right? So when for instance, you have a base station somewhere, you have your receiver here, currently you have reflections against all those walls, but if you have very smart coating using those intelligent surfaces, all those elements will work together so that they will capture all those waves and reflect them in a smart way in one point in space. So they act like beamforming, as we have seen, or kind of pre-coding, but in a very passive way, because they do not amplify the signal, they just reflect, but with a certain change that all the waves interfere constructively. And so this is what you end up with. If you have a transmitter with multiple antennas, you can transmit one signal, for instance, one stream to a given user that is pre-coded by a precoder at that base station with multiple antennas. And then part of the signals will go directly to the receiver. You have one receiver, so that's this HD. That's the direct path between the transmitter and the receiver. And then you can have another path here that is coming from the reflections against this smart reflector, right? So this is simplification of the system model, but what you have here, you have 3 parts. You have G, which is the matrix between the transmitter here and this reflector. You have theta that will characterize, that is a diagonal matrix typically, that will characterize those phase shifts that you have at each of those elements. And then you have H, which is your vector from this, all those elements to your single receive antennas. Okay? So this is also kind of smart repeater, smart relay, because essentially you have the signals is reflected in a certain way, and this performs some form of beamforming by changing those theta. And so what you want to do in this system, you want to design your W and your theta jointly so that you maximize, for instance, your SNR here, or you want to achieve a certain quality of service here and minimize your transmit power, or so on. Okay? So this is an example, and I will continue further on this this afternoon, right? So hopefully this afternoon the whole optimization will be over, and we still have quite a bit of material to cover actually. Okay? So this will be the topic of your coursework 3.